Okay, so hello everybody, and yes, and it's really a pleasure to welcome Pascal Oesch in Rome as our seventh Quid Ultra colloquium speaker for this 2022 edition. And this is really a fantastic closing talk before the summer break. And so Pascal received his PhD in 2010 from the ATH in Zurich before moving to the University of California, Santa Cruz as a Hubble Fellow. And then after a fellowship at Yale, he moved back to Europe in 2016 for a faculty position at the University of Geneva, where he's now an associate professor with a joint position with the Cosmic Dawn Center at the University of Copenhagen. And Pascal is an internationally recognized expert in observational research of distant galaxies. And he leads a group on the galaxy build-up at Cosmic Dawn. And his group focuses on understanding the build-up and the assembly of the very first generation of galaxies based on panchromatic observations. And he and his collaborators make use of very deep imaging and spectroscopy from space telescopes such as Hubble, Spitzer, and soon the James Webb Space Telescope, in addition to ground-based facilities. And using these observations, he has continually extended our cosmic horizon to the most distant galaxies, allowing us to trace the build-up of galaxies out to redshift 11, when the universe was only 400 million years old. And we really hope that this is going to be pushed even further back in time very soon with the first James Webb observations. So thank you, Pascal, for accepting the invitation, and I leave the floor to you.
Well, thank you very much, Raffaella, for this very nice introduction, and also thank you for inviting me. I'll take this off if that's okay. Yeah, so I just want to tell you a little bit about what we've been doing over the last few years. The thing is, though, we're 2 weeks ahead. Just in 2 weeks, there will be James Webb data. So maybe we can come back next year and we can see anyway. But I will show you a little bit of what we've been doing and how far we've come now with the current data sets. And so the big questions that we're trying to address is when and how did the first galaxies form in the universe? And also what were the physics that governed their build-up from these first stars up to the galaxies that we see in the universe around us today. And so I just want to start with a somewhat historical perspective now before we enter the James Webb era. So how far have we come with the Hubble Space Telescope over the last 3 decades, really, that HST has been in orbit? And so when Hubble was launched, it was in 1990, so 32 years ago, essentially. And at that point, we only knew about normal star-forming galaxies up to redshift 1, essentially. So here at the bottom, you see redshift red and the time after the Big Bang. And as you can see, only about halfway back the history of the universe, we knew about galaxies. And then, of course, Hubble had some problems initially, but with the first servicing mission, then a very deep observation was taken. That's the Hubble Deep Field North. And here it was really already clear immediately from this one image alone that the universe really was full of galaxies at very early times. And with the Hubble Deep Field, we could probe up to redshift 4 or so. And so the cool thing about the Hubble Space Telescope was that we had the space shuttle and we could upgrade the cameras continuously. And so that really made it was a big success. I mean, then in about 2003, the ACS camera was installed, and the next deep image was taken, the Hubble Ultra Deep Field that you probably know, and that really already now really pushed our observational horizon to redshift up to 7 with in combination with the NICMOS camera. And then since about 2009, that's where I started in this field. We now have the with-free IR camera that opened up the redshift 10 and above universe that I will show you a bit today. And so, with Hubble, we now have this amazing 2 megasecond exposure in the Hubble Ultra Deep Field, for instance. And we have multi-band photometry. With this, we can, of course, probe the distances of different sources. We have the morphologies of these galaxies. We can probe how they're building up as a function of cosmic time. And we're flying through the Hubble Ultra Deep Field here. And this red dot is one of the most distant sources that are known here in the line right now in the Hubble Field field. Again, that's about 2 millisecond exposure, so almost a full month of just observing this one particular field, and really that allows you to push down very faint to very faint galaxy luminosities. And so combining all of this together, I mean, I really like this quote from Edwin Hubble, T. Hubble, which is, yeah, the history of astronomy is a history of receding horizons. And that's really exactly what the Hubble Space Telescope has been doing for us, right, over the last 3 years. With all these upgrades, been pushing our observational horizon further and further back in time. And now, as you can see here, we can really probe into we can probe the galaxy population out to the first 1 billion year of cosmic history. And so why is this interesting? Why this 1 billion year is an interesting time? So I just want to, so that everyone is on the same page, just do a little bit of early cosmic history. And so here's the timeline. Now the time is running this way. So we have the CMB, the emission after recombination. The universe, of course, became neutral and was just a dark place for a few hundred million years, probably. And so that's what we call the dark ages. There were no sources of light after the emission of the CMB. And it took about 100 to 200 million years until the first stars were able to form and the universe really transitioned from a dark to a luminous place. But yeah, we don't know. That's only simulations can tell us. And from an observational point of view, of course, we don't know. But then as these first stars formed, they went supernova quite quickly, and then they started to pollute the intergalactic medium with metals, which then really set the stage for the formation of the first galaxies. We have much more efficient gas cooling. And so that we expect between 200 to 300 million years or so after the Big Bang, so 15 or 20 or so. And then as more and more of these galaxies started to grow, they started to emit ionizing radiation, so created these ionized bubbles around them that you can see here. And so create these Strömgren spheres around them. And as more and more of these galaxies form, at some point by redshift of around 6, these bubbles overlapped, and we created, and finished in this, what we call the epoch of ionization. So we transitioned from a neutral to an ionized intergalactic medium. So that's within the first 1 billion years. That's why we are really interested in this period. And so with Hubble Space Telescope, as I was saying, you can now really probe into this epoch and really probe how the galaxy population is building up during this early cosmic history. And the main, again, motivations for all this is, well, one, we want to understand this last major phase transition of the universe from a neutral to an ionized region space. Then I won't be able to talk about this much today, actually. But if you have questions, we can talk about this later. But then also, of course, these early galaxies are really ideal laboratories to test our galaxy formation models. I mean, we have a very limited amount of time available for different feedback mechanisms that we think are acting on the galaxy population at later times. So these don't have time to build up. And so it's really the perfect test bed, I think, for our galaxy formation and evolution models. And finally, we want to reveal our cosmic origins. I mean, after all, these are the building blocks of the galaxies later on, and that's where it all started in a sense, right? And so that's been a long open question, of course, trying to figure out where does this all come from. So those are our main motivations, but now let's see how we can actually do this. And so when we're observing the galaxies with the Hubble Space Telescope, for instance, here you have different filter curves shown here from the optical into the near infrared. So with Hubble, we can probe up to 1.6 micron or so. On the bottom, you see how the galaxy would look like in this kind of filter curves. And here in gray, you have the spectrum here for redshift 3 galaxy. And so as we go to further and further distances, so early and early cosmic times, what you can see is what's happening is that this break shortward of the Lyman alpha line becomes stronger and stronger. And the main point here is that we have more and more neutral gas in the intergalactic medium. This neutral gas absorbs in its rest frame Lyman series. And so you essentially really have a complete Lyman alpha break at redshift 6 or so as we enter the neutral intergalactic medium. Right? So it's not like a Lyman continuum break anymore, it's a Lyman alpha break at that point. And the main point here is that these sources are completely invisible here at optical wavelengths. So with the original Hubble Ultra Deep Field, we cannot really probe sources at redshift 7 and higher, and you really need this near infrared camera. That's what we've been working on, of course, over the last few years. And so if you let this go further to higher and higher redshift, what you can see is what's happening, right? We are really moving out of the sensitivity window of the Hubble Space Telescope. And so, by redshift 12 or so, we're really starting to lose completely the flux of these galaxies. And that's really the fundamental limit of what we can do today with the Hubble Space Telescope. And of course, that's why we need a next telescope to probe longer wavelengths to push further back in time. Okay, so, but over the last few years, I mean, as a community, we have been collecting large numbers of galaxies. Here is just, well, from 4 years ago, essentially, from Brad Salmon, a compilation from different types of surveys. We have very deep imaging, like I was showing you the Hubble Ultra Deep Field, or wider area data, like candles, but also other fields that make use of lensing magnification that you can probe intrinsically fainter sources. And so you can see here this compilation at redshift 6 and above, so the first 1 billion year. And so the main point to take away here is really that we have large samples of galaxies redshift 6 to 8 or so. And so, there we have, quite well in the measurements from different groups also agree quite well. But beyond that, as you can see, redshift 9 and 11, we only have a handful of sources at this point. And so our measurements become a bit more uncertain and so on. And so there's two reasons for this. Like one is intrinsically, I mean, the galaxy population becomes fainter and fainter, so it's more and more difficult. We're only probing the tip of the iceberg in that sense from the most massive sources at these sort of redshifts. But also in terms of our selection, technically it's becoming more difficult to select these kind of sources. We only detect them in one band, as you saw before, so it's a bit more difficult. So the current frontier with Hubble is redshift 10, 11, essentially. And we'll come back to these sources. So when we now look at the title of this talk is Panchromatic view, right? So when we look at the full ICD of a redshift 8 galaxy in this case, you can see the two main contributions, right? We have stellar and nebular emission that you can see here in blue. And then in pink, we have the reprocessed emission from the dust, from whatever gets absorbed into ultraviolet, gets re-emitted here as dust, and also atomic and molecular gas emission lines. And so if you look at the Hubble Space Telescope, where we select the sources in the first place, unfortunately with Hubble, we only probe a very small wavelength window, right? So it's really only the rest frame ultraviolet far UV, so typically around 1500 angstroms. So that gives us access to sizes, for instance, of this sort of star formation, star forming regions of these sources, but it's really only the unobscured emission of these galaxies. And so if there's a lot of dust in that absorbs this ultraviolet light, we will potentially lose galaxies completely. And we really have to pick them up here with longer wavelength information, like from ALMA, for instance. But also, so ALMA has been really a big instrument that we've been using over the last few years. Again, it's probing then this cold dust or cold gas in general, and the dust stream re-emission, so it really closes the energy balance of whatever's absorbed in the UV. We can pick it up with ALMA. But really, it's a combination with other facilities at different wavelengths that we get this a comprehensive view of the galaxy population. And for instance, with Spitzer, which unfortunately has been turned off, as you know, now. But Spitzer really has been amazing. I mean, in selecting this, in identifying the sources and really probing here the rest frame optical. And that's what you really need if you want to constrain stellar masses of sources. You really need information at longer wavelengths. And so, and as I will show, we also found strong optical emission lines actually with the broadband Spitzer photometry. And then the final kind of facility that we have is again in the ultraviolet, but it's then coming from ground-based, for instance, from the DLT, X-shooter, or Keck Mossfire or so. It's a near-infrared spectra which probe the rest frame ultraviolet for these sources. And I will show you just a few hints of different results that we have from this combination of Hubble and these different wavelengths now. But then, of course, yeah, James Webb is really going to clean this up, and in particular here probing from between 1 and here 20 micron or so, so in combination with mirrors, so really probing the full spectrum, and we'll come back to that in a second. So, okay, so first thing that we can do, right, we just, with the Hubble Space Telescope, we just count the number of galaxies that we have in bins of luminosity. You do this at different redshifts, and so you can really probe how the galaxy population is building up over the first 1 billion years. So here in red, I'm showing you this is UV luminosity functions. Again, the number of galaxies in bins of rest frame UV luminosity. This is at redshift 8, so that's 650 million years after the Big Bang. And then after redshift 4, it's 1.5 billion years after the Big Bang. And what you can see, right, is clear that the galaxy population is growing in number, which makes sense. So we're building, the galaxy population is building up and growing in terms of star formation. And on the bottom here, I'm just showing you the equivalent unobscured star formation rate from this ultraviolet luminosity from 40 or so solar masses per year, which are kind of the more massive Lyman break galaxies, to down to maybe 0.1 or so is kind of the limit that we can probe, including lensing magnification. And so we have a well-defined buildup of the galaxy population over this cosmic time. But then the important thing here really is that as we go to higher and higher redshift, these faint end slopes of these luminosity functions that become more and more steep. And that means that we are really seeing, so if you integrate this, right, that means that we have more and more faint galaxies below our current detection limits, actually. And so you're really only seeing the tip of the iceberg, high luminosity galaxies, in a sense, and there's a huge population, probably, of low luminosity sources out there, and we don't know how faint, we really have to push to see a downturn, let's say, in the luminosity function in the galaxy population. And so that's a big unknown, and James Webb again should help resolve this a little bit. Okay, then combining Hubble and Spitzer, as I said, Spitzer really gives us access to the rest frame optical already, even though it's a very small telescope. We have been taking lots and lots of data. All the Hubble fields, the extragalactic deep fields, have very deep Spitzer photometry as well. And so using the combination of these, we've been measuring stellar mass functions, for instance, out to redshift 10 as well now, like luminosity functions. And this is from our Stefanon's work from last year. And you can see again that, how the stellar masses now, so it's the same thing, so masses, and then here number density of galaxies in bins of stellar masses. You can see how the galaxy population is also building up in terms of stellar masses. And the really interesting thing here is then, once you have a stellar mass function measurement, you can use abundance matching and kind of connect, you can try to connect the galaxies to the underlying dark matter halo mass functions, or the dark matter halos in general. That's really what that's the ultimate goal, right? We know how dark matter is building up. We want to understand how galaxies are forming within that. And so, well, yeah, anyway, for now we have these constraints. So this is stellar mass, halo mass versus the stellar mass of the galaxies, again through abundance matching. And you can see, at least so far, we have no indications for a significant evolution in this relation over this redshift range in the first 1 billion year. I think at some point we expect there to be a deviation now as we go to very low metallicity star formation. But so far, at least, again, given the uncertainties, we don't see that yet. But that's something we'll be looking forward to, of course. Anyway, so combining these together, right, from the Hubble Space Telescope, we get the star formation rate as a function of redshift. On the other hand, we can integrate stellar mass density. So the stellar mass function, we get the stellar mass density. So you have on the right hand the stellar mass density in the universe as a function of redshift. So this is from a few years ago this is reviewed by Maddow and Dickinson, but it hasn't really changed much over the last year, at least out to these redshift 8. And what you can see is we have actually kind of a consistent picture of the buildup in terms of star formation rates, so the stars that are being formed, and the stars that we actually observe in the terms of the stellar mass in the galaxy population. So I would say that's quite remarkable. So this the black curve here is the star formation rate density, and if you integrate this, you actually get stellar mass density, the black line here on the right hand side. And again, you can see the agreement is rather remarkable. But the important thing to take away from here is that, by redshift 6, sorry, but after 1 billion year, at the end of reionization, we essentially have a similar star formation rate density as today in the universe, again, given that we have this peak. But in terms of stellar mass, of course, the galaxy population is still very, very rapidly building up. And you can see by redshift 6, essentially, we only have 1% of the local stellar mass density in place in the galaxy population. So the galaxies at redshift 6 are still in a very, very rapid growth phase, as you can see, building up both in terms of star formation rate, but also in terms of stellar mass. So in that sense, we cannot really expect the galaxies to look the same as galaxies in the local universe, obviously. And we can actually see this directly also from other evidence. And so I just want to look at a few key questions that were open. So first, very quickly, what are the physical properties of the first generations of galaxies that we can probe? Two, then I want to look at, well, how complete is our census actually of the galaxy population, given that we're selecting in the terrestrial ultraviolet mostly from Hubble. And then the last question, again, is kind of the big open question: when did the first galaxies appear in the universe? Okay, so let's quickly look at physical properties. One thing that I said we can measure very easily, in a sense, with Hubble is the sizes in terms of terrestrial ultraviolet sizes. And one thing that became very clear quite quickly when we saw the first images of with three camera is that these galaxies were at redshift 7, so in the epoch of ionization, were extremely compact. Just some indications for potentially these morphologies, but overall, if you combine all these sources together, they have sizes that are less than a kiloparsec in a sense. And so in the first 2 billion years, the sizes evolve as half-life radii goes 1 plus c divided by -1. And that's consistent with constant luminosity at the fixed halo mass. So kind of consistent with what we're kind of seeing from the stellar mass halo mass relation. No big change in that sense. But the really surprising thing, I think, over the last few years, really that we have found is that when we go to much fainter luminosities, so we make use of lensing magnification, we're finding that these sources are extremely compact. So there's an extremely strong relation between luminosity and mass, and size. So this you can see here. So this is the half-life radius now in parsecs. And so these are only for magnified sources using the foreground clusters. And so probing intrinsically very faint galaxies. And you can see this is a redshift 6-8 population. And here you have 100 parsecs. And so really the faintest galaxies are consistent, even though the error bars, of course, are relatively large, also because of uncertainties from the lensing. But for all of these sources, they're consistent with a half-life rate less than 100 parsecs. So kind of in the regime of sort of superstar clusters, really only. And Eros Anzella and others have been finding individual sources with spectroscopically confirmed redshifts, seeing exactly the same thing. And so, yeah, we're really seeing the first building blocks of the galaxies later on, right? It's extremely low luminosity galaxies, extremely compact. Then in terms of the other physical properties, in terms of, let's say, these galaxies are much more extreme. And we can see this directly with the broadband photometry from Spitzer. And so here, this is just a very deep view that we have with the Spitzer Space Telescope of the good south field, so including the Hubble Ultra Deep Field somewhere in here. And what you can see is that these galaxies really are extremely red in their Spitzer colors at redshift 8, but they're very blue at redshift 7. And so this is again from a few years ago, but the idea hasn't changed. I mean, if you stack all the redshift 7 galaxies, you can see that they have these very strange IRA colors of 3.6 to 4.5 micron. And then if you look at the same sources, but just slightly earlier at redshift 8, you can see that they have this type of color, very red in 3.6 to 4.5 micron. And you can explain this change in the colors really just by having these rest optical lines shifting through these filters. And then you can work out what is the equivalent width that we need for such a color change, and it turns out to be of order 700 angstroms rest frame. So it's really extremely strong, and less than 0.1% of local galaxies have such strong lines. So much more extreme than what we're seeing in the local galaxy population. Again, consistent with this rapid buildup. And we're seeing the same thing when we're looking at rest UV spectra. I mean, for instance, here, this is one source that we have observed with Lyman alpha, and then start following it up with longer wavelength spectroscopy and finding this very strong carbon-3 1909 emission. It's one of the strongest carbon-3 lines measured, you know, many sources now actually find for which we have spectroscopy in Lyman alpha and then REST UV spectra. We're finding these high ionization lines for many of these sources. And so it's when you put all this together, right, what this is showing is that the galaxy redshift 7 or 8, for which we can make these measurements, they're dominated by young stellar populations, so less than 100, 300 million years. They have high ionization parameters and low metallicities, but not too low, because otherwise you would not see, you know, the carbon-3 lines. And so, but yeah, so we're clearly seeing that these are just the building blocks of the galaxies later on, with very different physical properties. Okay. As I said, with ALMA, I mean, this really has been the big facility that we've been using over the last few years. One could fill a whole talk about just the results from ALMA over the last few years. So I will only give you a few highlights. So one, of course, with ALMA, we can probe emission lines. And for instance, here, C+ or O3 lines. And what we have been finding, for instance, that we can see quite a diversity in kinematics. So here is one example, it's probably a merger, but we also see potentially disks, rotating disks already at these kind of redshifts, or whatever disturbed morphologies or kinematics. Then we have found that, well, the ISM structure of these sources is much more complicated than we have thought. Sometimes it's not quite clear what is going on. This is an extreme example. Here, this is by Stefano Perniani a few years ago, finding that here's the UV emission that we see in this galaxy. And then he, you know, probing the O3 lines or ionized gas versus C+, which is photonisation region, so kind of neutral gas. You can see that there's complete offsets between all these different ISM for these different structures. And so it's not clear whether maybe there's an obscured galaxy sitting there somewhere, but nevertheless, there's this very complex morphologies. And finally, we have found very large dust reservoirs in some of these galaxies. This is an example by Tamura et al. Already 8.3, so you see dust continuum here. This is very difficult to explain, to have these very large dust masses, even in luminous galaxies early on. And Luca has been working a lot on this, of course. This nice paper where he's showing, so here is now different stellar mass versus dust mass. I have to say that the dust mass measurements at high redshift are, from our side, are quite difficult to do, but what you can see, different redshifts and different measurements from the literature at the time. And what Luca was showing is that, yeah, you need really very strong or rapid grain growth to reproduce these extreme dust masses at these very early times. So it's doable, it seems, but difficult, yeah. But so it's an interesting constraint, right? Yeah, but it's an interesting constraint that we will get both the metallicity buildup with James Webb in the future and combining this with the dust mass buildup. So yeah. Anyway, so let's move to the next question. Is our current census of early star formation really complete? And as I said, we're selecting off the REST UV. So, you know, if there's a lot of dust out there, you might be missing it. And so the big question is, what fraction of star formation is really obscured at these early times? And the big problem here is, so if you look, if you talk about obscured star formation, there's kind of three regimes, right? One was a completely unobscured star formation, so that the blue component that we can see directly in ultraviolet with Hubble Space Telescope. But then there's also the obscured component that is still detectable in the ultraviolet, and that we can correct for, actually. So we can use the UV continuum slopes that people have been using. But then the big question mark is, you know, what is completely obscured? It's just so much dust that we cannot see the source and pick it up with Hubble Space Telescope. And so that's a big question mark. And in particular, because at redshift 3, before ALMA, we didn't have a lot of ways to probe these, except for really extreme SMGs, some millimeter galaxies, but maybe what is the more normal population, we really don't know. And so, yeah, that's a big question mark, how much obscuration is out there. And so some authors have found that, measured, for instance, here, Carlotta Gruppioni with Alpine measured the infrared luminosity function at redshift around 6, so well, 5 to 6, and finding actually quite a high luminosity function, which then if you integrate this now, you get a measure of the obscured star formation density, and finding this to be extremely high. So I think one of her points, maybe one of these points is from her work. Because on the right-hand side here, you see now it's function of redshift, the star formation density, obscured versus unobscured. Yeah, as you can see, the different measurements over the last few years is a compilation by Jorge Zavala. You can see the different measurements disagree quite a bit. And by redshift 6 or 7, you have a factor of 20 or so uncertainty in this star formation density estimates from the obscured part. And so we don't know. But it's clear that we have been missing a few galaxies, and that there have been more and more of these samples coming along. And some people call them H dropouts, HST dark, or optically dark galaxies. And so they've typically been selected either with Spitzer, so the rest optical, or with ALMA. And so here's one example here from Christina Williams that serendipitously found this one source next to a main target with ALMA, and then following up this data found the source was detected with IRAC, but really only has mostly upper limits in terms of its photometry. And similarly, if you look at Spitzer data in these deep fields, you can see a lot of these sources that are very bright in Spitzer, but then completely absent at shorter wavelengths. So they're very red SEDs. Again, these HST dark sources, as they're being termed now, there's been a Nature paper by Tao Wang et al. Estimating the star formation density from these sources. Again, it's not redshift. And so it's more or less clear that they probably lie between redshift 3 to 6, even though we have very limited information, as you can see, for individual sources here. But they're most likely the high mass end of the galaxy population. And so overall, they might not contribute too much, in a sense, to the star formation rate density. You can see it's about 10% or so. But if you compare their contribution at the fixed stellar mass, so above 10 to the 10.5 or so, where the massive Lyman breakout population is very well. We don't have a lot of those sources. You can see that's essentially 2 orders of magnitude higher contribution from these sources. So we're probably still missing, the high mass end of the galaxy population, even at redshift 4 up to 6. And so yeah, we'll see what happens at higher redshift. And so what we have been doing over the last few years is working with this survey called REBELS, the Reionization Era Bright Emission Line Survey. That's co-PI'd Richard Bones, Valentino Gonzalez, Hannah Inami, and Stark, and 25 otherwise, including Rafaela and Luca here. And so we targeted 40 UV luminous Lyman break galaxies, redshift 6.5 to about 9 or so, that have been selected over 7 square degrees, essentially. So we're using luminous sources, and then scanned for their C+, so 158 micron emission line, or the O3 line, depending on the redshift, so the 88 micron. And at the same time, we're looking for dust continuum. And so it's a 70-hour large program, and it hasn't been quite completed yet. I think it's about 95% or so complete, but already now it reveals a lot of bright C+ lines for these UV luminous sources. You can see some of these already shown in Richard's paper, but also dust continuum emission for many of these sources. And overall, I think we have a 2/3. So for 66% or so of sources, we found C+ in emission. And if you now plot this here, this is a function of UV luminosity or absolute luminous magnitude as a function of redshift. You can now see here in red what the redshifts that REBELS has contributed in this field, and as a function of just number of redshifts as a function of luminosity, you can see that ALMA is really taking over in a sense from Lyman alpha, which is a typical redshift confirmation. And so in particular at the bright end, ALMA has been extremely successful now with this particular program, but also others in providing spectroscopic redshifts for sources, because so far we've only been looking at photometric redshifts mostly. And some of the most distant sources are really, now confirmed with ALMA. So in terms of emission lines in particular. So that's really has been an amazing development over the last few years. And really, ALMA has now finally been used kind of as a redshift machine, also as advertised in a sense. Yeah. Okay, so we've been using ALMA, these Rebels data in particular, to measure, for instance, the infrared luminosity function. So that's our measurements here. So it is now just again probing the function, infrared luminosity, the number density of sources. It's a bit tricky because it's a UV selected survey, so we have to make some assumptions. But what you can see here is if you plot this redshift 7 compared to lower redshift, we definitely see a very strong evolution. I mean, the error bars here are quite large from the Alpine survey, but it's in good agreement with several actually theoretical models, including the one here by Cindy in preparation. But again, so there's still some, I mean, something to keep in mind. It's a UV selected target sample. So if there's any extremely obscure sources out there, we will definitely not have them in our sample. And we actually know from Rebels itself that there are sources like that out there. And so this is a result that we've been finding as one of the earliest results from Rebels, actually, by my student Yoshi Fudamoto at the time. He's now a postdoc in Tokyo. But so we've been looking at two of these sources from Rebels. So the primary targets are in the center here. So this is a redshift 6.7. This is redshift 7.3. We found the C+ line for the sources. So these sources have been confirmed. And then as we looked at the data, in particular at the moment zero maps, we could see that, there's two sources next to them in the same frequency, strong C+ emission. And you can see this here, this one, Rebels 29.2, and then here we have Rebels 12.2, so 2 because it's a serendipitously detected galaxy. And you can see that the C+ line is exactly the same frequency as the central target. So, so it makes sense that these sources are associated with each other. But for both of these sources, the UV is completely absent. We have no detection anywhere except for the C+ and the dust continuum. Just one of them has a very weak Spitzer detection at 4.5 micron. So that was very surprising, but well, it also makes it more difficult to estimate their stellar masses and physical properties in general. So we only get upper limits in terms of stellar mass. We can estimate of the star formation rate, of course, from the C+ line, but also from the overall SED shape. But what you can see here is that these two sources, so these are circled in orange, the stellar mass versus star formation rate, they are consistent with being kind of on the main sequence, like the primary targets here, that this is fainter blue and red sources here, Rebels 12 and 29. But they are kind of an order of magnitude, more or less, an order of magnitude below the dust, other dusty star forming galaxies at these sort of redshifts, and also in terms of star formation rates, an order of magnitude lower. And so really they just look like scaled down versions of sub-millimeter galaxies, essentially very dust obscured, AV larger than 2 or so, but with factor 10 lower luminosities, but really consistent with being just normal star forming galaxies that have a lot of dust in them. And again, sources that we would have completely missed with our UV selections. And so yeah, it's proof really that normal star-forming galaxies have been missing from our sensors really, and we've been trying to estimate their contribution to the star formation rate density. And of course, that's quite uncertain and quite difficult. We have to include the clustering. I mean, these sources are clustered next to the brighter candidates in the center. But within a factor 2 to 3, I think uncertainty we can get an estimate, and you can see that it's kind of consistent or more or less consistent with these H dropouts that have been measured that I was showing you earlier. So that this population exists even out in the Apocophenese at redshift above 6. And so we can put this together now from the infrared luminosity function and from these two serendipitous sources. What are what is our estimate in a sense of the star formation intensity, of the observed star formation intensity. And that you can see here is of order 10 to 25%, even the error bars, of the unobscured star formation intensity. So it's not a huge contribution, most likely, but again, at the high mass end, I think it will be indeed quite important. And the main point here is, if we extrapolate this all the way to the low mass, okay, which I don't think is a good extrapolation, but it means that we could still be missing essentially 1 out of 5 galaxies in the epoch of ionization. At least at the high mass end, I think that is definitely true. And so, yeah, what is the way forward? Here, of course, we need terrestrial optical selections that we can do with James Webb in the near future. And we'll come back to that. Okay, let's change gear a little bit. So when did the first galaxies really form now? Again, unfortunately, we cannot, as I said, we can only probe up to redshift 11 or so. We cannot really probe directly the first galaxies at the moment. But what we've been doing over the last few years is really just, taking all the HST data that is available in the archive, really, and look for candidates at redshift 10, so the most distant galaxies that we can select. And so here's a compilation of all of these. So in the Candles fields, for instance, is a big extragalactic data set. We've only found 5 or so galaxies. Then we used the lensing clusters, which is called the Hubble Frontier Field dataset. Also there, we only found a small number. And so really in all the prime HST fields together, we only found about 9 or so reliable redshift 10 galaxy candidates. So it's a relatively small number. And then you can still, because they are actually found in different data sets, probing different luminosities, we can still derive a luminosity function based on these two sources. What we're seeing is that essentially quite a significant evolution from the redshift 8 luminosity function here that I've been showing you earlier. That is really quite well measured at that point. But here, of course, the uncertainties are quite a bit larger. And then we can also compare this to simulations. There's been many models out there. I'm only showing a subset of what we've been providing in the paper, for instance. But what is interesting here is that we are really at the low end kind of the predictions of the simulations. And we'll see whether that holds up again over the next 2 weeks. But yeah, so it's generally consistent, but really at the low end of the predictions. But when we now compute the star formation rate density based on this redshift 10 sample, we can put this again on this Maddow-Dickinson diagram. And so, put the point here at redshift 10, it's highly compressed, but yeah. And so we can see where this point lies that we're measuring. Yeah, so it's really an extremely steep drop compared to what has been measured before. And again, it also depends a bit on the integration limits of what you use, and Maddow-Dickinson used quite restrictive limits. So I think we know that there's more galaxies out there. So, but nevertheless, yeah, a significant evolution. And if you plot this a bit more, I change the axis a little bit, it doesn't look quite as dramatic. So this now as a function of redshift, the star formation rate density again, and you can see again from redshift 8 to redshift 10, there's about an order of magnitude decrease. And some people don't like it because there's, if you look at the lower redshift trends and you extrapolate this to higher redshifts, you would expect something like this. But in the end, it's the underlying dark matter halo mass function that is dictating what is happening. And that's actually also evolving rather rapidly. And that's shown here by this orange line. I mean, it's just a scale at redshift 8, but then just probing what is the evolution roughly of the halos that we expect our galaxies to sit in. And so that's actually in quite good agreement with our measurements. And so the big question then is, are we really approaching the dawn of galaxies, where if we extrapolate this, will we find a large sample of galaxies further on, further out there in the universe? And so we know at least one source out there at redshift beyond 10, and that's this galaxy here, GNZ11, that we've been finding a few years ago from imaging, and then we got spectroscopic follow-up with HST GRISM And you can see, of course, it's not the best spectrum that that one can obtain. That's why the redshift is also somewhat uncertain. Nevertheless, we've been finding this galaxy. There's also been spectroscopic follow-up with KEC, finding a similar redshift. So we'll see what James Webb has to say about the source. But the interesting thing is that this source is really extremely luminous for its redshift. So if you just measure the luminosity function bits of its one galaxy, it lies kind of a factor 10 to 50 higher from expectations from models at least. And so the big question is, maybe there's a lot of luminous sources out there. We don't know. Again, the cool thing about GNZ11 is that it's been detected with Spitzer also. So it gives us at least a rough estimate of its stellar mass and its radial solar mass is essentially at this sort of redshift. But again, that means that the first galaxy must have formed beyond redshift 11. So yeah, age of the universe earlier than 400 million years. And there may even be a source of redshift 13 now out there. This has been published recently by Harry Kane et al. This particular galaxy, now not using the Hubble Space Telescope, but using ground-based K-band. And so that's why you can see here in the K-band at 2.2 micron, you can still see this galaxy, and then it starts to disappear. So it would be outside of the visibility window of Hubble. So we cannot confirm or, the source with Hubble, but you can see it's detected in the K-band and then up to in Spitzer as well, like these two. But as you can see, also possible low redshift solution maybe possible. So again, we'll see. And they also claim a potential very weak O3 emission line with ALMA, which would put this at redshift 13.3 or so. But again, they will actually get spectroscopic confirmations with James Webb very soon. So we'll see. But anyway, so that would push the observational horizon even further, and the observation and the horizon of the first galaxies, of course, at least beyond redshift 13, right? But we can get indirect constraints really on the first formation of galaxies, also from the ages of sources. And so this you can see here, for instance, a lot of the redshift 9, 10 galaxies are detected with Spitzer, as I said, and we're actually finding relatively red colors, indicating that there's an older stellar population potentially in these sources, and indicating ages between 100 and 300 million years. And in particular, in this one source by Hashimoto et al., we know that the source has a redshift from O3. You can see beautiful confirmation. And so we know that the Spitzer band here is not contaminated by strong O3 and H beta emission. And so in that sense, we can, they can model this and see that, okay, there must be an older stellar population in there with an age of order 300 million years. Again, it's quite uncertain, of course. It's a very difficult measurement. But then that will put the dawn of galaxies beyond redshift 15. So meaning that, the first galaxies might have formed redshift at the age of the universe about 250 million years or so. Again, all of this will be improved over the next few years with James Webb. So I want to skip over some of these slides and just go to the way forward with James Webb. So James Webb really has been launched now finally at Christmas, and the first data will be released in 8 days. So it will be really exciting to see what will happen. But really, again, the main important point, two important points, and the main achievement will be rest-frame optical selections and rest-frame optical spectroscopy, and really that will be an extraordinary gain of information that we'll get. Again, you can see here now the filter curves from NIRCam only. You can really probe. First of all, you can push the observational horizon redshift 15 or however high it will be. But then also we can really probe now. Finally, we have complete coverage of the spectrum of the SED of galaxies from NIRCam. And then if you add MIRI on top of it, we can probe even further. And this is just a simulation, but again, it will be 100 times more powerful than Spitzer, so it really will be an extraordinary transformation of our knowledge. And we just extrapolate from what we have been observing with Hubble. We expect that with James Webb, we can at least push to redshift 14, probably 15 and higher, depending on, again, how the star formation rate density or the luminosity function is evolving. But then really the next gain is in terms of spectroscopy. And here we have just, the kind of emission lines that we've been using from the ground, like with Keck here, for instance, H alpha, O3, H beta, right? Are these the typical lines, O2, that, can be probed up to redshift 3 or so, particularly H alpha. But now with James Webb, this would just be, completely opening up the redshift space here, and H alpha up to redshift 7. With Miri, potentially we can go even higher. But really, whatever we have been able to do at redshift 2 or so, 2 to 3, we can now do at redshift 9, up to 9. And again, so we can ask exactly the same kind of questions that we have been asking at redshift 2. So what is the ionization state of the gas in these galaxies, the dynamical state, how quickly are metals building up? And so here, this is just a very easy simulation of redshift 7.3 source that I was showing you earlier. And again, because we know that these O3 and H beta lines are extremely strong, we should be very quickly get redshifts for these galaxies. And then in particular also for the brighter sources, if we integrate a bit longer with absorption line studies, like we can do now, redshift 2 to 3. So yeah, this would be really amazing. But the important thing here is that for this, for instance, for these absorption line studies, really we need bright sources, which will be quite rare. And so we have different programs that have been approved that I'm co-leading to try to really maximize the area of James Webb over the next few years. This one here is called Panoramic. So here we'll get pure parallel imaging of when someone is observing with near spec, for instance, we turn on NearCam to really get a big area, hopefully, over the next year or the next few years. And so with this, we can do resonant optical selection. So the sources, these H dropouts that I was showing you earlier, that are completely non-detected with HSD now, we can really probe their SEDs very well, and so get really good constraint on the stellar mass, the redshift. But then really, this pure parallel program is the perfect wedding cake kind of survey. So we can push out to the highest redshifts and select these kind of sources. So we'll see what happens. But then the next survey will be Fresco, that I'm also really excited about. And here again, we will make use of these O3 and H beta lines to really get a complete census of the galaxy population. We can really probe the 3D clustering of these sources, and finally also correct the broadband photometry for these emission lines on a source by source basis. So we get more accurate stellar masses and age constraints and so on. So we indirectly confirm when the first galaxies are formed. And so, yeah, just to finish with, really James Webb is just the first next step in a sense. Really the next few years are really a golden era of early universe science. We'll have Euclid hopefully launching very soon. We have on the US side, Roman, we have moons coming along, multi-object near-infrared spectrograph, again from the ground, but then ELT, SK, and all of these facilities really, first galaxy is a key driver for these and the early universe. So over the next decade or so, we'll have a huge wealth of data, and so looking forward to come back maybe in a few years. So I just want to finish again with this. The history of astronomy is a history of receding horizons, and again, with Hubble, we have come a very long way, further than we actually expected, I think. But then now the big question is how far will James Webb bring us over the next few years? So yeah, I'll just finish with a summary, and thank you very much.
Thank you, Pascal. It was wonderful. This, amazing, and it's really. I should have invited you in 2 weeks.
Yes, I know.
But maybe you wouldn't have had the time to go through the data yet. So a lot of exciting science. I don't know if there are questions here. Yeah, I see 2 hands rising. Let me ask even from remote participants if there is any question, please write on the chat or raise your hand, and we'll give you soon the opportunity to ask a question to Pascal. So Luca.
I have two questions.
No, I think that you have to speak louder, otherwise they don't. No, you can stay there, but just speak louder.
So when is this fresco stuff expected to get data? Immediately or in some stuff? What is the timeline of these two panoramic?
Panoramic. Yeah. So the
panoramic,
first.
sorry.
Yeah.
And fresco.
Yeah, no, it's a good question. Yeah. So fresco will be observed in November. And then February, so 2 fields, so that will be done. And yeah, we should get some data soon. But then panoramic, we don't know yet, unfortunately. It's a pure parallel. And so in principle, we can observe all the time when someone is not, requesting the parallel. But there seem to be some issues with data downlink, with GWST are producing a lot of data, and so they don't have enough time to download it. And so they're a bit worried. And so we'll see whether, so at the moment, before September, we won't get any data with panoramic, but hopefully it would be a huge loss if we cannot just turn on the camera whenever we can.
Yeah, sure.
Take data. So, yeah.
Okay, thank you.
So at least vacations are okay.
Yeah.
The second one is about your question on where star formation started, basically.
Yes.
So where the first galaxies. And you were showing this extrapolation of the trend at lower redshift. You can show it. That would be.
Seems like I can easily go. Sorry.
That one.
Yes. Okay. Now we have to do this.
Now, falling star.
Yes, sorry.
That's really
Okay.
Yeah, about this extrapolation. First of all, I mean that's a super complicated process. Extrapolating is always a dirty stuff. So I believe that the second version maybe has more sense. But maybe we have to change our idea of what a galaxy is.
Yeah.
Maybe there's a lot of star formation and very small inaccessible structures. It's very diffuse. It's very small mini halos, and it's peculiar or very low metallicity. So when you push the redshift, I mean, at these values very high, back in time, I mean, the assembly is still in progress, at least from what is predicted by simulation. So probably it's not a galaxy in the sense that we understand it right now. It doesn't have any structure, but you could still have a lot of star formation, peculiar star formation at low redshift, very diffuse in space, in very small, non-assembled structures.
Yeah,
so I don't believe that extrapolating is.
No, I mean, here again, this is, this is only down to our current kind of detection limit.
Sure.
So it's not, again, we're not going into the background almost, you know what I mean? But it's also true that, again, for the sources we're seeing that they're quite compact. At least, again, we're getting into the territory of star cluster complexes. So, but that, again, that only with lensing we can assess that. Because actually with lensing, I mean, you expect that, if there's a high shear region, you would expect the source to be arced, right? You would expect the shear, but still there in these high magnified regions, we only see a very compact.
But with the JWST, we are expected to observe some well-known field-rich lens.
Yeah.
So probably more structures could emerge. I don't know.
Yes.
It's interesting.
Yeah. No, indeed.
So there is do you mind, Ruggero, there is a question from the chat. So you can read it before.
Okay. Before Planck 2018, the low E data, the tau was inconsistent with the luminosity density measurements. Now that the low E suggests lower tau, everything becomes consistent. But yeah, GNT11 being 10 to 50 times more luminous poses a problem, doesn't it? Yes, I mean, so in terms of Planck, I mean, in terms of reionization, indeed, we had this big problem, right? That we had reionization very early, and there was just not enough galaxies out there to drive it. So in that sense, the tension has become much easier. I mean, there's not big tension anymore. We still need a lot of ionizing photons from the galaxies out in the intergalactic medium. But with 10 to 15%, you can make it. But then, so in that sense, just having one, very luminous galaxy is not necessarily a problem for this. In particular, if you look at this, indeed, in the y direction, that's sort of a problem. But in the x direction, it's only half a magnitude essentially off. And so if you have, I mean, again, I don't know, but if you have some sort of AGN activity potentially in the center of it, you can easily boost the luminosity. Or if you have Percy star formation, you can move off the luminosity function. I think so. I'm not sure. I'm not too worried about this particular source at this point having any problem with Planck, but indeed it's interesting. And then if you find many more of these bright sources, I mean, it starts to become a problematic. Yeah. So because it will show that the star formation has to be quite efficient very early on in massive halos, at least. Yeah.
So Ruggero had a question.
So regarding sources at redshift higher than 10, I wanted to ask you, what can we possibly say about the metallicity of stars, if we can say anything at all? And what do you think we will be able to say with JWST data?
The metallicity of the stars.
Yeah.
Okay, so the question was about the metallicity of the stars. With James Webb, it will be very difficult. As you can see, in terms of the gas phase metallicity, no problem, because of emission lines. But for the stellar metallicity, you need absorption lines measurements like this. I mean, yeah, different wavelengths, but yeah, that will be quite difficult for the stellar metallicity. Maybe through stacking, we may be able to do something. But maybe, yeah, if you have very luminous sources, you can start to get some constraints there.
So, what would be the redshift limit from which we can say something about the metallicity of the stars?
Yeah, I mean, I would say, I don't know exactly, but before the redshift data, I would say, yeah. I'm not quite sure what are the lines that you need to grow. We can look into this, but no, I mean, again, you need absorption lines. That's the main problem, and so you need bright sources. And so near spec is very good, but again, for this one, this is one of the most brightest galaxies, redshift 8 or so. But with 20 hours only, you can get sort of absorption line information. But then, yeah, to do that at longer wavelengths, it starts to become more expensive. But maybe if there's a lens source or something like this, yeah. But I think it would be in a handful. I mean, not a large number of not like a maybe large number of sources. But for the gas phase metallicity from these strong lines, no problem. Yeah.
Any other questions from the remote audience? No. So okay. So.
So I'm from very different people. I'm students. I'm really basically not
Great.
even topic. But I wanted to ask. I didn't understand well. So if there is a more redshift, then there is more likely the galaxy from the ionization era, or it's
So the higher the redshift, yes. So at redshift 6 and higher, we're into this ionization epoch, where the galaxies, I mean, at least in our current understanding, I think galaxies are producing the ionizing photons that are then ionizing the universe. But we don't know 100% again, because in particular of these escape fractions, so we need the ionizing photons to get out of the galaxies into the intergalactic medium. We know there's POC3 stars, the first generations of stars, and there's also potentially AGN that can contribute. Yeah.
So that's why we're also interested in this low redshift, because it's possibly like we can rescale everything. Why we are interested in this low redshift?
You mean below redshift 6 in general?
Yes.
Yeah, I mean, we are trying to find analogs in a sense of, so we cannot directly measure the ionizing escape fraction. Let's say it's the number of ionizing photons making it out of the galaxies in their ionization, because those photons get absorbed. I mean, by definition, they are ionizing the universe. And so you have to probe lower redshift to find analogs potentially, and find kind of other measures to maybe correlate with the escape fraction, for instance. Yeah, that we can then potentially use, for instance, with NearSpec in the future directly in the
Kazu?
Okay, so yeah, my question is also related to one of them. So about the realization photon budget. So with JWST, so that we can observe around the realization epoch and until down to very low luminosity galaxies. So do you consider that we can conclude that we can solve the ionization source problem?
Yeah, that's a good question. I think
The
so.
wizard.
Yeah.
Pascal is a wizard.
No, I mean, this escape fraction will always be the big question mark, in a sense.
Interpretation rate, those are higher. Yeah, galaxy. Be sure even with how it can be estimated.
Also at lower redshift, up to redshift 3 or so, we can directly observe the ionizing photons coming out, which are then shifted to the UV. But then at higher redshift, because of the Lyman alpha, because of absorption in the IGM, it gets more and more difficult. And so
and then no indirect way to estimate.
But that's what we're trying to do exactly. So with Daniel Scher, for instance, in Geneva, we have this program for redshift 3 galaxies where we know that ionizing photons are coming out of the sources. We're like doing different diagnostics, including these kind of lines or other, like the O3 over O2 has been used as one of the possible correlations with Lyman continuum escape and so on. Lyman alpha, for instance, but then you have the other problem about intergalactic absorption of Lyman alpha again. So there's a magnesium 2. Anyway, there's been quite a few number of possible tracers, let's say indirect tracers, yeah. But we have to calibrate them at redshift 3 or so.
So one last question.
No. I have to ask it.
Yes.
Assume that there's a way to constrain the escape fraction when it's too difficult. Any chance to at least constrain the sizes of ionized
Yeah, I mean, again,
like the proximity stuff.
Well, we
do tracers.
I mean, so there's different ways, right? One is the easiest. The solution is SKA. So coming
2027.
exactly
We have to wait a little bit.
coming in a little bit longer time scale. But then the other thing we're trying to do now is, for instance, we have a few of these Lyman alpha emitters that, I mean, the one at redshift 8.7, that in principle is supposed to be in a neutral intergalactic medium, yet Lyman alpha is coming out. And we actually can see that there's sort of all the densities around it. And so, yeah, so kind of doing the topology of different Lyman alpha emitters. Yeah.
Ionized problem.
But then, of course, you will never, I mean, you always have to make the assumption it's a nice round thing,
Right.
Which it won't be. So
How do you do expound?
In fact, my
modeling, but
yes, exactly. But I think the Lyman alpha statistics, yeah.
So I see there are other. Oh, sorry, I missed to look at the chat.
But I think it's what you had earlier.
Okay,
Just
so then
here I
it's
haven't
fine.
opened it, yeah.
So no. Oh, thanks for explaining. Okay. So my very last question is something which sometimes so it occurs to me as a thought. So do we have the right tools to interpret JWST data? Because this is, I mean, we really kind of use sometimes the oversimplified description of the star formation history of a galaxy.
Right.
The way,
Yeah,
do we have the right tools? So aren't we risking to bias our interpretation of the data because of our limited tools in interpreting the data.
Yeah, I mean, there's many different aspects, right? That
Yeah.
that you're trying to constrain. But yeah, it's a principle star formation history is now indeed. Well, yeah, for these, if you want to extrapolate back, right, for the star formation history of these galaxies, you need to make some assumptions about
Yeah.
how they built up.
But even to estimate the ages of the
Yeah, no,
stellar
exactly.
populations, or even when you were mentioning the beta slopes,
Yes,
and we know, from the few resolved observations that we have now, that if you have, non-post-spatial emission of infrared and UV photons, then you're gonna be significantly biased in your interpretation of what you observe. So this is something we should all keep in mind.
No, no, absolutely. But also when we start to interpret these emission lines, not these long to strong lines and so on, I mean, we have to make the right models, right? Because the
Yes.
ionization conditions will be different. We know that already, and so
Yeah.
on. And the metallicity will be lower, and so on. Yeah. So
Maybe the IMF will be different.
probably the IMF will be different.
And
indeed,
that's a real mess.
No, indeed, but yes. But I'm confident that we have enough data that we can start to work these things out, right?
Yeah,
At least
sure.
over the next few years. I mean, not maybe in the beginning, but
Yeah. Okay, so
Okay.
thank you so much, Pascal,
welcome.
again, for lots of things to think about. And I thank you all for attending from remote, and have a nice summer, and we will see in September, October for the next talk. So goodbye. See you.
Everyone.